All right, I'm recording. So last class, we looked at Newton's first law, not just equilibrium of forces, but equilibrium of torque. And we said that that could be for an object with no rotation at all, or maybe it's rotating with a constant angular velocity, okay? So this idea that torques are balancing, we saw with example 1, where you have a meter stick and then added masses. Where you put the mass matters, okay? And so I told you B and C. I want you all to try those. And so we're going to take a look at D. It's got some change to it. And so we'll do D and then move on from the meter stick. So here, our unknown is this force on the right. And notice it's at an angle. And so angles are important to torque. Remember, optimally, we want what relationship with our force and lever arms? We want them to be parallel or perpendicular. To open a door, you pull perpendicular. So here it could have an X and Y value. And so if we use the meter stick or the rod, whatever rod, beam rod, then we can actually look at the vertical component, so FGY of that force. Now, where's the 30 degrees? Well, that component is also this side of the triangle, 30 degrees with the horizontal. And so this unknown force that we're trying to find, it has a sign relationship, not sign because that's what the formula chart shows, sign because the perpendicular or Y component is opposite the given angle. Yes? And so I can make a trig function, or an expression here, that Fy, or perpendicular, is equal to the hypotenuse times sine theta. Now that's going to be needed to do either now or later. I'm going to incorporate it into my torque statement. And so let's look at the torque by that perpendicular force. And so if it's a vertical Y component, the lever arm, and how to identify a lever arm is going to be a skill. Hopefully practice makes better. It's from your axis of rotation to that line of force. So I'm going to darken in right here, vertical component, our perp would be 6 to 10 or 4, what we'll call meters. Everyone good with that force? The last thing to decide about this particular force, what direction of torque does it have? Now, let me rephrase that. It's not gonna rotate. So you may say, well, it has no torque. It has no net torque. But this force alone down on the right wants it to rotate what direction? Clockwise. And so you take that vertical component and kind of wrap around the fulcrum. That triangle is going to be your axis of rotation. And that would lead to a clockwise torque. Okay, so we can't do that without looking at all the others. So let's look at the other side. We've got 2 kilograms, which is going to be a downward gravitational force. And it's down on the left. So if you wrap around the pivot, it's going to be counterclockwise torque. What would the lever arm for that 2 kilogram be? Well, it's from your line of force to the axis of rotation. And so I'm going to just darken in. Hopefully y'all can distinguish there. Vertical force, horizontal lever arm. What would the lever arm for this one be? 6. Is it -6 because it's on the left-hand side? Is lever arm a vector? No, it's a distance, scalar distance. The direction of torque is coming from the force, how it's oriented with your axis of rotation. And so we've already determined the direction of torque. Okay, next force it shows is the 50. And so that one's already drawn in. If you want, I can, color it in there for us. And so it's down on the left. That's also going to be a counterclockwise torque. lever arm from the force to your axis of rotation. R perp for the green would be 4, right? 2 to 6. So 4 meters. And then we have the 6 kilograms. And so we've got a down force here. So FG6 down on the left, counterclockwise again. You okay? Okay. And then the lever arm, I'm trying not to overlap them, but we're just going from that area, that line, that plane of the axis of rotation to the line of force. And so 4 to 6 would be a lever arm of 2. Okay. All right, so we've got 3 counterclockwise, 1 clockwise. Balance of torques, not just the forces, okay? Forces balance, but torques balance separately. But wait, there's one more, the forgotten torque. Let's not walk away before we consider the what? The center of mass for the board, the rod itself. Up above, they said, your rod has a mass of 4 kilograms. Now in example A, it had no torque. Why? It's not because it didn't have a force, it's because it didn't have a lever arm, because the center of mass existed at the fulcrum. But now in B, C, and D, where's the center of mass for your rod? Well, assuming it's a uniform plank or rod, it's going to be there in the center, 5 meter mark, but it's not the same place as our fulcrum. And so we do have a gravitational force of the rod. It's going to also have counterclockwise, lots of counterclockwise, goodness. And then what's the lever arm? Well, how far away is it from the axis of rotation? 1. Oop, not 1 centimeter, 1 meter. Everyone good there? So it wasn't drawn in, but you don't want to forget to read carefully. By the way, some problems will say a massless rod. Okay, that means you don't have torque in the rod itself. Okay, it's not significant in that situation. But here they gave it to us, the mass. We have to determine if it matters. All right, so we've got all the forces, the lever arms, and the direction of torques. So now, if these are all going to stay in place, maybe nobody rotates, the torques are going to balance. And so let's do our setup. Torque counterclockwise equals torque clockwise. So that's an application in Newton's first law. So clockwise, we had the red. And so I'll just try to go in order here. And so we had the weight of the red times its lever arm. Again, symbols before numbers. Then we had that applied force times its lever arm. Then we had the 6 kilogram force, which is a weight, FG6 times its lever arm. And then we had the rod, which has weight, and its lever arm. So it's a lot of counterclockwise torques. That's okay. It's possible. All equals this new applied force, or a secondary applied force. That's what we're looking for. And remember, the actual force is a hypotenuse, but it's only the vertical component that leads to torque. And so I'm going to write F sine theta. So that's the component matching up with our horizontal lever arm, the R perp of whatever it is. Everyone good with setup? And so now let's plug in the numbers that we know. And I'll go back to red. 2 kilogram times gravity times its lever arm of 6 plus the applied force, which was given as 50, times the lever arm of 4. Yes, when you come back, let's focus on physics, back group. Thanks for the offer of vanilla wafer or mini Nilla wafers and Milano cookies. And oh, how great do we feel? Okay. And then we've got the gravitational force of the 6 times gravity. Its lever arm is 2. And then the rod itself, if we scrolled back up to the top, they told us the mass was 4. And so times gravity, and its lever arm of 1. And the last bit, we're looking for that F, that's a hypotenuse. Sine theta, we know, is going to be sine 30. And then the lever arm is 4. So the numbers aren't the challenging part here. It's getting them in the right place. It's getting them figuring out who belongs with who in terms of direction. And so hopefully the numbers are 120 plus 200 plus 120. And then sine 30 is 1/2. So half of 4 is. And so work it out. Let me know what you get. If there's not a calculator at your desk, they were charging over the weekend, so go grab one. Let's see, we get 480 on the left over 2. Is that right? 240 final answer? Yes, okay, good. So it's a big force, that's okay. Alone, it's responsible for the clockwise torque. Okay, questions on a meter stick balancing equilibrium type of question. Correct. Yes. So for the purple, the one that was at an angle, I could have extended the line of force because that's kind of what we did whenever we had grid lines to help. But then you'd have to make sure you got the right perpendicular and you'd have to figure out, well, where is that 30 and what function do I do with that distance? And so to me, do whatever you see first, but to me, it was easier to just focus on that Y component that's already perpendicular to the bridge, the board itself. As long as whatever you're multiplying together has a perpendicular relationship, you should be good. Right. So earlier in part A, our rod's mass, the weight of the rod, didn't have a torque because it existed at the hinge or at the fulcrum. But here they do have a separation. And so again, if you think about that line of action being where that force is, you want a horizontal distance to the vertical force. Okay. Okay, the last one on this page doesn't really relate to the meter stick application, but it is a torque equilibrium. And so, you know, pulleys are coming in our future. We can apply torque to pulleys, forces, and energy and momentum. And so pulleys are a big deal in the grand scheme of things. This is just a, let's keep it all equal, 2 forces, not huge math, but they tell us there's an outer and an inner radius. So previously, we've really only dealt with pulleys that have a single disc. Well, if I want different amounts of torque, maybe I have different levels of your inner outer radius, okay? And so both of these are going to rotate about a center point fulcrum or axis of rotation. And I'm just going to redraw for one of them. I don't want my picture to get too cluttered. And so both of them have a force that's basically tangent to the circle. And so if this is a force in the vertical direction, where's the lever arm? Where's the lever arm for this force? From your axis of rotation to the vertical force would mean it's a horizontal distance right here. Well, if you're dealing with a cylinder or a disc that's circular shape, isn't that lever arm going to equal the radius of that disc? And so what they're showing us, I have two discs. The radius of the outer disc is twice that of the inner. Now they don't give us numbers, but couldn't we say the inner is 1 and the outer is 2? As long as I play the correct proportion game, yeah. And then the force that we're pulling on the small one, it's down on the right-hand side. And so it's going to wrap up or wrap the fulcrum, what direction? Clockwise. The weight of the 4 is going to wrap down on the left. So it's going to wrap the other direction. And so the numbers aren't bad on this one, but recognizing that this torque on one and the torque of the other are equal. So we have torque equal, but we've got one with a radius of 2, one with a radius of 1. Let's get them in the right place. And so the smaller radius to an unknown force is clockwise. And then the force of our 4 kilogram would be 4 times gravity. And it's got twice the radius. And so when your radii have a 2-to-1 ratio, your force has to have a 1-to-2 ratio, right? And so our final answer to either keep this at rest with no rotation or rotate at a constant angular velocity would be 80 newtons. What if I pulled 81 newtons? Would I be in equilibrium? No, we're going to have angular acceleration. We're going to have changes to the angular quantities, right? And we go back to that kinematics or Newton's second law of rotation. What if I pull with 79? Same thing, I'm going to have change, but in the opposite direction, okay? Okay, next page has 3 prompts. We're going to do 2. I'll do the top 2. Number 3 is very similar to number 1. And so here's a meter stick here. Now, if it was really long, I might need help supporting it. So in the spirit of this top question, okay, imagine I've got 2 supports, whether they're 2 separate people or my 2 hands. I'm not going to make it all symmetrical. We'll offset it, right? And so what's the normal force at the A and B locations, whether it's 2 people or 2 hands? I have 2 unknowns. How am I supposed to solve for 2 unknowns, right? Well, let's see. So we're getting into maybe a system of equations, more than one equation. And so let's draw a force diagram for the system. Now, technically your object is the board, okay? And the rule of thumb is, what do they give you the mass of? If the people were standing on the board, they'd have to give us the mass. But here, they're just the prop. Their hands are just holding it up. And so each of them has a normal support force. What direction? Up. And so I'm just going to say FNA. And then we have FNB. And right now, we don't know which one's bigger. We could take a guess. Hopefully, that's an educated guess based on what we know of physics. But let's say we haven't thought about it. These are the 2 unknowns. Any other forces acting on the board? Gravity. Where are we going to draw the gravitational force for the board? Center of mass. That's the CM there. And so we've got this gravitational force. Now, the people have mass. They have weight. But like I said, this one is not, they're not standing on the board. Okay, that comes later. And so, gosh, it's just forces. Couldn't we use forces to solve? I mean, isn't it true that your up forces balance your down forces? We could find the weight. Could we just say, well, if it's a weight of 100 newtons, couldn't we say each person supports with 50? No, okay. By the way, it's not symmetrical, so it's not 50-50. If they were each holding, equal increments from the center of mass, that would be true. Can we take a guess who's going to support more of the mass? B. Okay, let's prove it. And so I have two unknowns here. Let's use torque, okay? Now, clockwise, counterclockwise, we need a fulcrum. Did they say where the fulcrum was? No. Now, sometimes there's strategic locations, and that's what this question is going to do. So your strategy, when you pick where to put the fulcrum, okay, is to put the fulcrum or hinge or axis of rotation, whatever you want to call it, at an unknown force location. I have two unknowns, put it at one of them. Because what kind of torque do you get if you put it at an unknown force location? In other words, what if we put the fulcrum at person A? That's not a person, wearing clothes there. That's our fulcrum, our axis of rotation. If I put it here, there is a force, but the strategy is there's 0 lever arm, 0 torque. And so that's the strategy. You want to zero out one of those torques. And so put the fulcrum at an unknown force location to 0 that torque. Again, it still has a force. It's just not providing a torque when you put your fulcrum there. Now, no one's going to rotate, okay? But it's about the would-be rotation relative to that fulcrum location. And so let's take a look. Gravitational force is down on the right side, so it will wrap around clockwise. Fn of B is up on the right. Wrap around the fulcrum, that would be a counterclockwise, okay? I would say try to refrain from being like, oh, they must be opposite, okay? Because if you have it drawn wrong, maybe you picked a wrong spot for the fulcrum, okay? It should work out. And so we know that the torque of the normal force B is going to balance the torque of gravity. Each one has a force, each one has a lever arm. Let's identify the lever arm. And so lever arm for the gravitational force is what? From the force to, not the center of gravity or mass. You want to go to your axis of rotation. And so the force exists at the center of mass. It's a vertical force. I need a perpendicular lever arm. And can we get a number here? They tell us the whole length of the board is 10. Assuming it's uniform in mass distribution, then the center of mass is at the center. And our magnitude, assuming a person is all the way at the end, would be 5. What about B? What about that little bit more? It's a vertical force. Your lever arm would be horizontal again. And so R perp for B would equal what? 6. And so each of those forces, each of those lever arms, let's plug it in. And so the normal force of B, that's what we're trying to solve, or one of the things. Lever arm is 6. Equals the force of gravity. They say it's a 10 kilogram. So I need to multiply by gravity, right? mg to get our force. And then the lever arm would be 5. And so 500 divided by 6. Let me know what you get. 83. We'll stop there just to make future math a little easier. But yeah, 83 newtons for the person at the B position. So FNB. So what about FNA? Plug it into what? To the first one. So if you remember, equilibrium of forces is still true. So if we go back up to the top, we know that the total down force is 100. One of the up forces is 83. And so what's FNA? FNA should be what? It should be about 17 newtons. And you may be thinking, oh, but it can't be that easy. For your system, your secondary, it can be, okay? Now, what's another option? Okay, we'll do this quick, so stay with me. What's another option? Move the fulcrum to another place so that a person has torque and you can solve for their unknown force. Where am I going to put it? Well, you can put it at the center of mass. You can put it at person B. Technically, you could put it on the end that no one's touching, the total right side. So your fulcrum location is relative, okay? Now there's strategic parts. If you put it at one of the forces, then there's less to work with. But now imagine A is the only one we don't know. So where do y'all want to put your new fulcrum? And I'm going to redraw the picture so it doesn't get cluttered. Do we want to put it at the center of mass location or at B's location? Which one? Center mass. And so I'm going to quickly redraw that just to sketch. And so if we put the fulcrum at the center of mass, then we now know that your B force is right here. We know it's 83 newtons, and we're trying to find FNA. Lever arms for each. Lever arm would be 1 meter for the 83 newton, and then it would still be 5 meters for your A force. Put these torques equal to each other. Notice they're both up, but one's on the left, one's on the right. And so we're going to have FNA times 5, balancing 83 times 1. What's 83 divided by 5? 16.77, right? And I had rounded the other number. Same, right? So about 17 newtons. Same. So yeah, your second calculation, it can just be forces, or you can do another torque rotation or equilibrium solve, but you got to move the fulcrum so that your unknown has a torque. Good deal? Okay. That one is very similar to number 3, but instead of 2 people supporting the weight of a board, you've got a person on a bridge or something that's held up by 2 cables. Determine the tensions in both cords. So instead of 2 unknown normal forces, you're dealing with 2 unknown tensions, but your approach is going to be very, very similar. So I'm going to have you try this one later. Okay. Again, we don't have time to work every single problem. And so we're going to take a look at the middle one. This is the walk the plank type of scenario. Okay. So whether or not you know who Indiana Jones is, somebody was just having fun. Okay. And so it's a person. They're walking out on a board. That board happens to be on a cliff. Don't try this at home. And then, of course, we want to keep them safe. So the question is, how far out can the person go from the edge of the cliff before the plank tips over? And so when the person's on the left side of the plank, is there any worry about tipping? No, but as they get further and further and further, they're going to reach a last moment of equilibrium. That's really what this is. It's the last moment of equilibrium, because one more tiptoe and it all tips over and you have rotation. And so this is the last moment of equilibrium. How far out can he walk and still be safe and get the treasure or whatever? Good deal? And so, bless you, We've got a person on a board. So look at your system. What forces are acting on the system? Gravity of who? They gave us two masses in our prompt. Are they both important? Notice I said the word system a while ago, right? And so the board has mass. It's going to cause a downward force, which may or may not give us torque. And then the person has their own mass. Again, a down force may or may not cause torque. And so, by the way, I don't know if I said it last time, but as we draw these force diagrams, notice it's different than October. Are we just putting a dot and putting all the forces? No, we're putting the forces where they happen. By the way, if you don't do that, you can't get lever arm, at least as easy. And so that's why when you're doing a rotation question, you want to draw the forces where they act. And so Indiana Jones, the person, has a weight. So FGJ, the weight of Jones. And then we also have the board. The board has mass. Where am I going to draw the board's weight? From the center of mass. It is a true statement that, the left side is going to be different than the right side, maybe. If you look at some's hanging off the cliff, some is not. You can do it separately, but y'all, you get the same answer as saying, well, the center of mass right here is collectively, okay, the mass of the board. And so FG of the plank. Now to do, yes, go ahead. Good question. So in order to figure out torque, we need to identify where's the best strategic place to put the fulcrum so that we can determine lever arm to determine rotation. Now you might be thinking I've got two down arrows. It's got to be somewhere in between. That's correct. But let's fast forward that tiptoe moment when rotation occurs, okay? And so the last moment of equilibrium, go forward in time. Isn't it true that at some point your board may shift like so? Okay. The last moment of contact with the cliff is right there at the edge. Okay. And so this last moment of equilibrium before it shifts, this is where we get a maximum normal force. So, and again, without the rotation, you may be thinking, well, it's touching the ground. I have a whole bunch of little normal forces. But as he goes out further, normal force is going to maximize at the last point of contact, which would be the edge of the cliff. Everybody good? So that's why I put the fulcrum, the triangle. By the way, I don't know if I said it earlier. Center of mass, I like a dot. Fulcrum, I like a triangle to make them different. Okay, some of these problems are going to have a dot for both. And to me, that's just a little confusing. Dots all over the place. So now that we have a fulcrum identified, can we identify the lever arm for each? And so go back to Indiana Jones. It's a vertical force. The distance horizontally from the axis of rotation to the line of force. Hey, look, it's what they have labeled X. And so R perp for Jones is actually what we're solving for. How far can Jones go from the edge of the cliff and still be safe? And so that's going to be our unknown. What about for the weight of the rod or plank? From your axis of rotation, from your fulcrum to the line of force, R perp for the plank. Oh, to get those numbers, what do we got to do? Well, let's see. It's 10 meters long, so center of mass is at the 5 meter mark. And you know that 5 meters is on the right side as well. Oh, we needed to read one more thing. It says 3.5 meters of the plank hangs off the edge of the cliff. That doesn't mean X equals 3.5. It means 3.5 includes X, but plus some. And so with those numbers, what's the lever arm for the Planck's gravitational force? Five minus 3.5, 1.5. And so 1.5 meters for the Planck's lever arm. Okay, so the big concept here was about normal force maximizing the fulcrum strategic location at that edge of the cliff. The math isn't going to be hard. All right, let's talk wraparound. Who's going to torque what direction? Okay, well, first of all, that normal force maximum is going to have how much torque? Normal force max passes through the hinge, so it'll have 0 torque. Yay, because that's an unknown force. By the way, in the future, what if they say find the normal force at the hinge, right? You could maybe use forces, you maybe could use torques. But Jones down on the right is going to be clockwise. Planck is down on the left, counter. And so it's those two that are going to balance. And so the torque of the Planck is going to balance the torque of Jones. FG Planck times lever arm Planck equals FG Jones times lever arm Jones. And you don't have to, but if I take it one more step, variable, mass of the Planck times gravity times the lever arm equals mass of Jones times gravity. If you take it this far variable wise, what do you notice can happen? G on the left, G on the right. You could cancel G. Everybody's in terms of mass. We're not trying to isolate or solve for a force. And so we can do that. You don't have to. And so plug in what we do know. Mass of the Planck, they said, is 150. Times the lever arm, we said, was 1.5. Mass of Jones in the prompt said he was 100. And then the lever arm of Jones, we said, is really the X that they're trying to get us to solve for. And so, work it out. What do we get? How far out can Indiana Jones walk and not tip over? And don't try and use the little grid lines on the Planck to guesstimate, okay? You want to prove your physics. They're grading your torque. .25 is from Indiana Jones's force to, just a reminder, lever arms are not measured from center of mass. It's with the fulcrum or hinge or axis of rotation. And that's the answer. They said, how far from the edge of the cliff? We put the fulcrum at the edge of the cliff. So that is our final answer here. Questions on walking the Planck, two unknown forces, how to solve for both? So y'all are going to try Indiana Jones on the bridge, solve for those two tensions, right? Torque and forces, torque and forces. Let's move on to page 7. Okay. Page 7 has several pictures here, and it's all about identifying lever arms, what forces are doing what kind of torques, and the goal of these 4 is just write the net torque statement. And so maybe or maybe not they're in equilibrium. That's not told to us, but a net torque statement. Because guess what? Just like with forces, we wrote F net statements, we're going to write net torque statements. Sometimes we're in equilibrium and it equals 0. Sometimes we're not, and you get an angular acceleration. And so here it says that assume these different objects below are hanging from the pivot, which is like a nail through the pivot. And later they say it's the black dot. So here's where I'm just going to come in here and make them all triangles. Okay? Because maybe the dot is the center of mass, but maybe it's not. And so I'm going to come in here, my personal preference, fulcrum triangle, dot, center of mass in normal situations. And so for this first one, you know, when you go to a restaurant and they have memorabilia nailed to the wall, okay? I don't know where, but sometimes they'll have old records nailed to the wall, right? So I think of that. I've got this circular disc. We're going to take a nail through the center, boom, 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 into the wall. So maybe it's not falling down. Maybe we push on the top of it. And since it's one nail, maybe it can rotate, right? Well, it all starts with a force diagram, where the forces originate. And so we have FA being pushed at the top of the object. What other forces are acting on this object? And I say forces plural. Gravity, assume everything has mass unless told otherwise. So how do we draw gravitational forces? From the center of mass, which for a circular object is probably in the middle. And so from the center of mass, we draw the gravitational force. Now, yay, that's where the nail is. That's our fulcrum. Is gravity going to lead to any kind of rotation? Is it going to have any torque in this problem? No. And so, hold on. So the torque due to gravity is going to be 0 because the lever arm of gravity is nothing. So the force is there, but there's just not going to be any torque. Any other forces? Remember, I said it's not falling down. Something's got to hold it up. My applied force is not in the upward direction. So remember, they put a nail there. Isn't there a support force from the nail? And whether you call it support, nail, pivot, fulcrum, or you call it normal force, because a nail can be a surface, but you're going to have a normal force here, or F nail, where the nail is, which in this one is also the fulcrum. So what's the lever arm for the nail? If the force exists at the pivot point, lever arm is 0. So the torque due to the nail is also 0. So it's there, it's a force. They could ask you to solve for the force, but it's not going to lead to torque since they said your fulcrum is there. And so goodness, gravity and nail provide no torque. Let's look at FA. FA is this horizontal force. It's not passing through the fulcrum. And so a horizontal force needs a vertical lever arm. And since it's a circular object, the lever arm would equal what? The radius of the circle. So it will provide torque. And on this one, it's the only one. And so net torque would be FA times the lever arm R. That's it for the top left. Now let's change shape. What about the top right? What if I have a triangle and they put the nail in the very bottom and then we're going to push it to the right? Now, won't this probably, with one nail, isn't it probably going to rotate in the future? Okay, it'll probably rotate in the future. And I'll look at, fast forward. We'll draw the diagram after we draw this one. So what forces are acting? Once again, we're pushing on the applied force. It's not going to pass through the hinge. So line of force, it's a horizontal force. The lever arm from your fulcrum to the force. What is our lever arm for the applied force? Half H. And it's going to cause what kind of torque? We'll wrap around. It would be a clockwise torque. What other forces are acting on this object? Gravity. Now, I need to identify the center of mass because center of mass is not located. It's a triangle. It's pretty symmetrical left, right, but is it symmetrical top, bottom? Probably your center of mass for this is going to lie where? Closer to the top, if we look at the triangular shape. So maybe our center of mass is right here. And this is where we're going to draw the gravitational force from. Notice it passes through the fulcrum. And so right here, right now, does it have a lever arm? No. Does it have a torque? No. Technically, there's one more force. Why is the whole thing not falling down? There's a normal force due to that nail. What direction? Up. I draw it from the nail, which also is at your fulcrum location. So what's the lever arm for your normal force? 0. What's the torque in normal? 0. And so on this one, it's again just the applied force that has net torque. And so net torque would be the applied force times its lever arm, which was H/2. That's it in the present tense. Would you agree it's going to rotate because of this? Fast forward a couple seconds. And so maybe sometime in the future, after it's rotated a little bit, wouldn't you agree that maybe our triangle is not so symmetrical left, right? Notice applied force could remain the same. You could push along with it. Normal force is still going to go through the pivot, but now your gravitational force, wherever it is there, is not going to pass through the hinge. So just moral of the story, just because in the present tense, gravity does no torque, in the future it could. In the past it could. These are snapshots in time, forces and torques. So your lever arm on that one would be from your fulcrum to the line of force. You'd have to know angles, you'd have to know more dimensions in order to figure that one out, okay? But the lever arm would not be 0 in the future. So R perp for gravity would not equal 0. And so the torque would not equal 0 either. Good on that point? I just don't want you thinking because one problem, gravity has no torque in this situation, that it always will. That's not true. Okay, we're actually going to do bottom right next. The one on the left bottom actually is going to continue with math on the bottom portion. And so this one, again, just force diagram, identify lever arms, and then do your net torque statement. And so once again, we have an applied force. And it's not going through the fulcrum, so let's identify its lever arm. So again, you can extend the line of force. It's a horizontal force, which means you need a vertical lever arm from fulcrum to that line. And so what variable are we going to use for the lever arm for the applied force? H. It's a full H. By the way, do you always have to push something at the very, very top? Could we have pushed halfway up? Could we have pushed 3/4 up? Sure. What other forces are acting on this object? We've got gravity, and so we draw gravity from the Center of mass, we'll assume uniform in mass distribution. So I'm going to try to center my center of mass. Gravitational force. It's a vertical force. So we need a horizontal lever arm from your fulcrum to line of force. And so what would the lever arm for gravity be? 1/2 W, half the width. Good deal. What other forces do we have? We've got a normal force. What direction? Up. And so it's going to happen where? Oh, let's get to this. This is a little bit of a special case. It's kind of like walking the plank. And so if I push on this object, why is the fulcrum on the right bottom and not the left bottom? Well, and my cart's on wheels, so you'll just have to imagine. But if I didn't have wheels, if I push on the top of an object, isn't it possible that it grips and then it just tips over? Or, you know, wheels help. I can push and it slide, it slip, right? And so here we call this tip or slip, and we'll spend a little bit of time with the math later, but this is called tip or slip. And it's based on how much friction you have, okay? Yeah, you could say it's the nail, but later when we put this on a floor, maybe we do that here to start, we put a floor here. If I push more and more and more, in the future, isn't that left side going to come up a little bit? Isn't normal force going to maximize at that far corner? Okay. And so normal force is going to be at the pivot point, and I'm going to write it as normal force max. Okay. And I can put it in Canvas or try and show you later. We'll do some math later on behind tip or slip. But there's actually a website that shows the animation or sequencing of how the normal force goes from equal at all places with the floor. But then when you start pushing on it, it maximizes on that far side. Okay. Well, if we're on a floor, or you can look at it as a nail, there's going to be another force. Because if I just look at the forces, I'm pushing to the right. What's going to prevent it from moving to the right? Because if you have one horizontal force and nothing to balance, it's going to move. It's not just going to rotate, it's going to move. And so there's got to be some kind of left force. And so whether you call it the nail or friction, there's going to be a leftward force to help balance. And so again, just not wanting to overlap. So you could say friction or part of that nail. Normal force would be due to the nail or due to a surface. Me adding the floor kind of takes the point away from the nail. Either way you look at it, a nail having an upward and leftward force, or you've got a normal and frictional force, both of those forces have what kind of torque? No torque. And so the torque of your nail normal is 0, and the torque of your friction or nail in the horizontal is 0. Because they both happen at the fulcrum. They both pass through the hinge. No torque, no lever arm. So our net torque statement is going to read what? Well, actually first we need to swoop. We need to see which one is going to, or do they have the same direction of torque? And so go back to the applied force. It's to the right above your fulcrum. So keep that dashed line wrap around. It's going to have clockwise, but the orange gravitational force is down on the left. It's going to wrap around counterclockwise. And so maybe it's balanced, maybe it's not. The point of this one is writing net torque statements. And so what would our net torque statement read? Oh, wait, clockwise, counterclockwise, those are different directions. Doesn't one have to be positive, one have to be negative? Now, true story, I could do whichever one if they don't tell me. Let me go, in X, Y, left, right, we have standard sign convention. Here's your standard sign convention for rotation. You ready? Imagine you're looking at a 4-quadrant grid. Quadrant 1, 2, 3, 4. Make it a circle. What's the standard positive direction? Counterclockwise. So counterclockwise is the standard positive direction. And you're like, but on a clock, it goes clockwise. It's not based on a clock, it's based on the quadrants. Okay. And so I'm just going to go with it. Clockwise would be the negative direction. But at the end of the day, you have to pick one, or they pick one, and you follow suit. Okay. And so net torque would be the torque done by your applied force minus the torque done by gravity. And so we'll keep those going. Torque applied would be your applied force times its lever arm, H, minus mg is the gravitational force. And why did I go here? You could start FG, but you usually put your final answer in terms of givens. So they gave us mass. And the lever arm is half the width. And this equals net torque. That's what they wanted, just a statement. So that's our final answer for now. Good? Okay. And then we shift to the left. Now, whether it's a sign that's connected to a building with a string, or what some videos or practice problems call a drawbridge, that's kind of dated now, but think about the medieval days. You had a castle, you got to protect it. You put some moat water around it, right? When your friends come up and say, let me in, you lower the drawbridge so they come, right? How do you do that? You've got this cord or chains probably back then that you would unroll or roll up. And then enemies come and you say drawbridge up. We're looking at it at this moment. What's the net torque? Now notice there's no friends, there's no people on the bridge or the beam, right? And so what forces are acting on this bridge? Force diagram, it all starts with a diagram. Gravity is drawn from center of mass. So I don't have that. We'll assume it's uniform in length and mass distribution. And so here we've got our center of mass. And it's not necessarily drawn to scale here. I'm trying not to clutter my forces. What other forces are acting on this bridge? I've got a normal force. Where? Let's save that one. Let's save that one. There's another force. There's tension. There's a string. Now you see a capital T, and y'all know I don't like that for tension because we just came off a period. And so I'm going to call it FT. And it's parallel to the string. Where is it pulling on the bridge? Well, it's connected to the right end. And so I'm going to trace basically parallel to string that tension force from the right, and it's pulling up and to the left. Now you mentioned normal force. Where's this normal force occurring? At the pivot, right? On the wall. So maybe this is a wall over here. Okay. And the bridge is attached right there. That's the pivot point. Well, based on forces, if you have a down force, something has to hold you up. Do you think it's going to be tension alone, or do you think that hinge is going to help? The safest assumption is to say, well, I think the hinge is going to help. And so maybe we've got this force of the, pivot in the y direction. Well, the string is pulling this bridge leftward. We don't want it crashing into our castle, so the hinge is going to provide a rightward force. And so we've got a pivot force in the x direction. By the way, on the AP exam, the most recent years, you actually are told, do not draw components. Now, this is our first one, so I'm going to keep it as components, but how would you simplify these x and y components into one resultant force? It'd be a diagonal, right? Instead of north and east, it would be a northeast. Okay? And so on the AP exam, you would draw just that one. Good deal? And so there's three forces: tension, gravity, pivot. And so how many are going to do torque? Well, the pivot goes through the pivot, right? The hinge. And so how much lever arm is the pivot point going to have? 0. How much torque? 0. What about the gravitational force? It's down on the right, so it's going to wrap around for the clockwise direction. Where's its lever arm? Well, it's a vertical force from the pivot to that vertical force. It has a horizontal, and no numbers yet, but if you have the whole length of the rod, it would equal half the length. And then we have the tension force. Oh, there's an angle. Yuck. Okay, so let's talk angles. They gave us theta against the wall, right? Where's theta with tension? Well, actually, and again, there's more than one way to take this. I look at the drawbridge like, ooh, the lever arm is the full length of the bridge. So I actually say, let's use the whole thing, R perp for tension. I'm going to make the whole length a horizontal lever arm, meaning I need a vertical component of that tension, because the vertical component is perpendicular to a horizontal lever arm, yes? Now, if we think about, well, that's a vertical plane, just like the wall, alternate interior angles. I think I'm using correct verbiage. The wall is vertical, FTY is in a vertical plane. And so the tension, I don't think bisect is the right word, right? But it connects the two parallel lines. And so alternate interior angle, there's going to be equal to theta. So with that, that vertical component is going to wrap around in the counterclockwise direction. But with angles, you want an expression. And so notice FT is the hypotenuse. If you need to see a triangle, you can connect your X. What trig function is going to help us get FTY? It's hypotenuse tension times it's going to be cosine theta. And that I'm going to highlight. But Ms. Earhart, the formula chart says sine. Okay, I warned you whenever we studied work, parallel forces and distances, but sometimes on a ramp, you got to use the perpendicular. And so sometimes, you know, sine theta for torque is a most of the time, but here's an example where you got to do cosine theta to get the vertical perpendicular component of the force. Okay. And honestly, at the end of the day, it's because they gave you the angle with the wall. If they'd given you the angle with the drawbridge, we would have used sine. Okay. So just, it's all where they put and define theta. All right. Net torque statement. We know who's doing torque. We know what direction. And so I'm going to make my positive, the counterclockwise, and the clockwise negative. Just go with the standard unless there's a reason not to. And so net torque is the torque of tension minus the torque of gravity. Plug in my forces and lever arms. And so for tension, it's the vertical component. So Ft cosine theta times L is your lever arm, minus mg is the gravitational force, and the lever arm is L over 2. And right now, that's your final answer. Questions on the drawbridge, the forces, the lever arms, the angle. Oh, start over. Why did I count Ft? Oh, the pivot goes through the hinge axis of rotation. So it has no lever arm, it has no torque. It's a force. If we made a force statement, it would need to be there. But based on where the fulcrum is, the hinge, we don't have any torque. So if you put it in the torque statement, it's not really clockwise or counterclockwise, but maybe you put a plus, torque a pivot, but it should zero out. Okay, so now that we have a net torque statement for this drawbridge, now number 5 says, well, based on that picture in the bottom left, it's on the same page in this packet. If what if the mass of the bridge is 200 kilograms and the angle is 40? What is the tension? And then later, what is the force of the pivot? So we're going to solve for these two unknowns. So I've got two unknowns. To get it started, we want to make sure we have the pivot at one of those unknowns. It's already solved, or we already have an FNet statement based on the pivot itself having the fulcrum. And so now we're just going to use that equation to solve for tension force with one change. We got to assume it's in equilibrium. And that's a safe assumption, because if it wasn't, they'd have to give us some of the angular velocity or angular displacement, angular acceleration. They'd have to give us a little more information. And so if it's in equilibrium, net torque is going to equal 0, meaning the torque of tension is going to balance the torque of gravity. So it may look a little different, but it's the same. I'm basically adding the torque of gravity to the other side. And so we end up with Ft cosine theta L equals mg L over 2. And no one raised their hand and asked, how come they gave us the mass but not the length? Again, in physics, if they don't give you a value and you know it has to be used, chances are it's going to what? Cancel out. So L does cancel out. The ratio of 1 and 1/2 is still there. And so now we can solve for tension. So plug in cosine 40 on the left. Mass is 200 times gravity, and then all over 2 there. And so, they couldn't pick a better angle, but make sure your calculator's in degree mode. Let me know what you get. Don't give me every decimal. You don't want 10 decimal places, right? Rounding on the AP exam, 2 or 3 non-zero digits. So 1,000. Say again. Yeah, I'd probably, 1305, 1,305. You'd probably be okay using 1,300, but I'm going to keep the 5 because we may use this answer to get B. And so I don't want to error carried forward too much, but don't put 20 decimal places after this, okay? You'll lose a point on the AP exam if you put every single number from the calculator, okay? They want you to have an appreciation for sig figs. Okay, so now we know the tension. Y'all, this is the hypotenuse. because we already took into account the component with the cosine 40. And so this is the hypotenuse. We solve for the hypotenuse. What is the force of the pivot? And so now we want the force of the pivot. We can go into forces now that we know 2 out of 3. So there's 2 ways to do this one. So FYI, we can do forces, but you got to remember that it's in 2 dimensions. We'll have to write F net X, F net Y, and then maybe end with Pythagorean theorem. Or we can do torque again, just move the fulcrum. So I'm going to leave it up to y'all. Y'all tell me which way you want to do. Do we want to go forces exclusive, or do we want to do torque again? And they both have their own level of simplicity and or complexity. Somebody vote. Oh, option 1. Okay. I thought you were like, wait for the answer, wait for it. Okay, number 1. And so if you want, you can try to move the fulcrum to one of the other places, solve for your unknown torque from the pivot, take into account direction and such, but we'll use forces. And so I mentioned the 2D. And so remember, we've got up, down, left, right. With forces, you have F net X and you have F net Y. And so horizontally, we had tension in the horizontal, and then your pivot also had a horizontal force. Vertically, we had tension pulling up, we had the pivot probably pulling up, and then we had gravity pulling down. Now, if you're in equilibrium of forces, F net in both cases is going to do what? You're not accelerating, so F net equals 0. And so we want to solve both of these for your pivot components, okay? And so in the horizontal, FPX is going to equal the tension's horizontal component. Well, let's go back up. Now that we know the hypotenuse and the angle, let's take a look at that tension triangle. If we want the horizontal component, that's opposite theta. We'll use what trig function? Sine. We want the x component. And so we'll write it in terms of hypotenuse ft times sine theta. Well, now we know the tension force, 1305, and then we have sine 40. And so get me what that equals. Degree mode, and you can round. I think it actually rounds to a very nice, pretty number. Or maybe I'm thinking of the y. I'm thinking of the y. The y is a pretty number. Tell me what the horizontal is. Yeah, that one's not as nice, but we'll take it. So 839 newtons is the horizontal component of your pivot. Now let's pause, do the vertical. So your vertical forces, 2 ups, 1 down. You can solve for FPY, add gravity to the other side, minus FTY. FG equals mg minus that vertical component. So earlier we saw it was adjacent. So we said it's hypotenuse times cosine theta. Then we can plug in our numbers. The mass of the bridge, they said, was 200 times 10 gravity minus that 1305 times cosine 40. And so just to save a little bit on time, 1305 cosine 40 comes out to be about 1,000. That's the nice one. And so 2,000 minus 1,000 is 1,000. Now, first of all, my first conclusion to look at, so the two angled forces have the same magnitude of components, right? Y'all, wasn't this one pretty symmetrical? The pivot is on the left side, the tension is on the right side, and the center of mass is in the middle. So vertically, it's symmetrical. So each of your up forces is supporting half the weight. By the way, it's not always this case. What if your string is connected anywhere else other than the very end? Then you're going to have some difference, okay? So if you're looking at the numbers and you're like, oh, it's coming out so pretty of numbers, it's because it was a symmetrical setup. Next time, maybe Indiana Jones is crossing the bridge. Maybe he's in the middle, maybe he's not. And so that's going to add to. And so now we know the two components. Now what can we do with FPX and FPY? And so one is 839 to the right. The other is 1,000 in the upward direction. How do I find the resultant for your pivot? Well, now hold up. How do we get that? What's our next mathematical step? Pythagorean theorem. And so 1,000 squared plus 839 squared equals our answer squared. Work it out. Let me know what you get. You get what? 1305, but that was our tension force. How can the pivot be the exact same? Again, it's a symmetrical setup. Newtons, correct. 1305 newtons. So again, don't start thinking, oh, it's always going to be the same. We'll add mass, we'll move the string. Maybe, and here's where we're going to end, we're at least going to get it started. Maybe it's like page 8. Our drawbridge, maybe it's now just supporting some kind of sign, okay? It doesn't actually have to be a drawbridge, but I've got a beam, it's at an angle. The string is now horizontal, and we're hanging an additional mass. So it's the same feel, but there's a difference. Good deal? So on page 8, determine the tension force in the horizontal cable. And so FT in the horizontal cable right there. And we're going to attach a 420 Newton mass to the end of it. And the beam itself is 20 kilograms as shown. So it all starts with a diagram. What are the forces acting on this system? I'm going to start with tension since I already started with blue. Remember, tension goes from where it's touching the beam parallel to the string. And so tension is, I'm going to move that up a little bit. So tension is right there. What other forces? Gravity of the block. Now, true story, the block has weight, which pulls on that little string, which then the string pulls up on the block, but then it pulls down on the beam. Y'all remember Newton's third law, right? And so if you take a system approach, at this point of contact, don't we just have that 420 Newtons? And so we've got that 420. If you want to call it FG of the added mass, you can. I'm just going to keep it at 420 since they literally gave us the Newtons. Don't multiply that by 10. Yes. Yeah, because if you take a system approach, this is fine. You don't have to break it down into internal forces that cancel out. Oh. You can tilt your axis. If I think that's where you're going. I'm not going to just because we're still early on. Okay. But maybe you could. I think you're still going to have to do geometry either way. There's no, you see 15 degrees in there. There's no way around it. You're doing geometry somewhere. So I'm just going to keep it as is. What other forces? There's two more forces. They gave you the mass of the beam, the bridge, the rod, whatever you want to call it. So it has a gravitational force, and we can assume it's in the center. And so find your center of mass, straight down. I'm not going perpendicular to the beam. I'm going to keep in the typical XY coordinate system. And then the last force that's there, it's a force, is what? The normal force at the pivot, the hinge, whatever you want to call that. Now, we've got two down forces. True story. The hinge has to have some kind of upward support, yes? We've got a left tension force. Doesn't it have some kind of rightward force? And in the spirit of AP, don't draw components. That up and right is going to go together. And I'm only drawing it bigger like this, so I'm not like cluttering up. So this is not necessarily drawn to scale, but I have this pivot force, hinge force, normal force, okay? And so we're trying to find this tension. Well, I technically have two unknown forces. I don't know the pivot force. So think about that strategy. If you have two unknowns, where am I putting the fulcrum? The axis of rotation? Put it one of your unknowns. Well, we don't want to put it at tension. I'm trying to solve for tension. And so what if we put it here? Now the pivot goes through the fulcrum. How much lever arm does the pivot have? 0. How much torque does the pivot have? 0. The force is there, but there's no torque relative to this location. And so let's do our wraparound and lever arm for everybody. Tension is going to be to the left above, so it's going to curve counterclockwise. Notice it's a horizontal force, and so I'm going to have a vertical lever arm. And so our perp for your tension, ooh, yuck, trig, right? Because if you think about a tension triangle, they tell us 0.7 meters is where it's attached. They tell us 15 degrees. And notice that perpendicular portion is opposite theta. And so our perpendicular is going to be the portion 0.7 hypotenuse times what trig function? Sine times sine 15. So go on and get that for me real quick while we're here. And again, if you were like, oh, I should have tilted it to put everything reference the beam, then your force would be at an angle. So you're going to have to do angles either way. 0.7 times sine 15 is? Point 18 meters. We'll use that later. Let's at least get them drawn. The last two forces that have torque are down on the right. Oops. And so they're going to have clockwise. Clockwise. They are both vertical forces. So let's think about horizontal lever arms. And so from your fulcrum to the line of force, so our perp for gravity, now careful here, I'm going to draw this one separate. And so for gravity, we know that from the fulcrum to the center of mass is 0.5, right? And here's the lever arm we want. Well, if you think about parallel to tension, parallel here, think geometry, another alternate interior. This angle down there is 15 degrees. What function are we going to use to get the lever arm for gravity? This is your hypotenuse, not sine. Oh, okay. Sorry, I thought you said sine. So again, there are some times where just because the formula chart says sine, you got to look at your actual labels. And so our perp G is going to be 0.5 times cosine 15. 0.5 is the hypotenuse, okay? Get me that number and we'll be done for today. We'll do similar on the added mass. What's 0.5 times cosine 15? 0.15? Well, I don't want to use the exact same, so 0.48. Yeah, I want to show that I've done something different. Okay, we'll pick up here next time. This one is not as easy, right? So maybe you've noticed we're leveling up, okay? Next time, we'll continue with some torque practice and get into more moment of inertia. It's okay, I was just joking. I
There you
don't
go.
want one, I promise. I can't-
Bribery is different than.
No,
kindness.
I can't, no bribes, but I count calories, so it's not
Oh,
worth it
that's
to
fair.
me. You know, the whole added sugars.
That's all right.
So my coffee creamer is my splurge for the day.
All right.
Okay, but I do appreciate the offer.